Hello RustConf! Welcome to Paris! Today I'll be doing you a bender and go, fine, I'll just make my own stable ABI. It will have blackjack and compact sum types, and it will run on stable Rust. But first, some introductions are in order. My name is Pierre Vital, I'm a senior technologist at Zscaler, and I spend most of my time working on Zeno. Zeno is a data-centric networking middleware that unifies data in motion through publisher-subscriber semantics with data at rest and computations through distributed queries. Zeno is many things. It's an open source project under the Eclipse Foundation. It's written entirely in Rust, and as such, it's of course blazingly fast. In fact, it's 1 or 2 orders of magnitude faster than the competition. There's also an embedded C client for places where you can't take Rust yet. But most of all, Zeno is flexible. Its self-healing network can be linked with anything from IP transports such as TCP or TLS to non-IP links such as serial, Bluetooth, shared memory, anything you like, really. Zeno is also very happy to interact with other technologies, other pub/subs, databases, or even just the web in general. The way Zeno does that is through plugins, and as the designer of its plugin system, I've contended with ABI a lot. So how do you make a good plugin system? Well, there are really 2 schools of making plugins, and the correct one is IPC plugins. With IPC plugins, you just spawn your plugins in different processes and use IPC channels to communicate between your plugins and your host. That's going to provide you great isolation because, well, your plugins are in a different process, which means if they crash, your host process is safe, and you can even attribute different permissions to your host and your different plugins if the OS allows so. It's also going to get you one step closer to getting RPC plugins, remote procedure calls plugins, which are going to let you relocate your plugins to another machine if you need more computing power, for example. But there's one problem with IPC plugins, which is that you need to communicate, and to do so you need to serialize messages and throw them over some form of communications, both of which are going to have overheads. Otherwise, you can choose violence and go with dynamically linked plugins. These are typically the ones you think of first when you think of a plugin. They're not so great for isolation because they have none whatsoever. You're just literally loading foreign code into your own. But you do get direct memory access for everything, so you're going to be very fast, and that's why we use them in Zeno, because if we wanted an IPC plugins, we just use Zeno as the IPC transport. But dynamically linked plugins have one problem. You need to be ABI compatible with your host. If you're not, undefined behavior is going to rear its ugly head, and things are going to go very wrong very fast. So now I've said the word 3 times, and like Bloody Mary, I now have to tell you what's an ABI. ABI stands for Application Binary Interface, and it's basically API's older sibling, where an API lets you specify what you can do with a library, what types are available, what functions are in there. An ABI is about how you do things with the library, how you call the functions, how types are laid out in memory. And by you here, I meant the CPU. So an ABI is built really of 2 things. The first one is the calling convention, which is just a big answer to the very big question, how do you function? To figure that out, you need to answer plenty of tinier questions. Who says which registers? Because both the caller and callee functions are going to want to use registers if they want to do any computation. But caller is going to get very angry if callee clobbers its registers and doesn't restore them when caller expected it to. Callee is also going to wonder where its arguments are. Are they in registers? Are they somewhere on the stack? If so, where are they? In what layout? How is callee supposed to return values? And how is caller supposed to call callee? Most of the time in x86 you'll just use the call instruction. But I've heard of some weird calling conventions where you'd use a different instruction to call a function, or even interrupts. Finally, there's exception. How do you make sure that unwinding happens properly when something has gone wrong down the stack? All of these questions are very interesting, but typically they require 100 pages of documentation to answer and a deep knowledge of assembly, which I don't possess. So instead, we're going to look on the other side of ABIs, type representation, which is about how you lay out your types in memory. There are different kinds of types. The most common is a structure, or product type if you like math. Typically, you're just going to ask yourself how are fields ordered and whether or not they're aligned. Alignment is a rather low-level constraint, which has to do with how CPUs read memory. They don't actually do it byte per byte or bit per bit. They do it by chunks, and these chunks are typically going to be aligned to some memory address. So if you want to read an integer, you better be within one chunk if you want to read it in a single stroke. So if you're at the end of a chunk, like here, with the dashed line representing the joint between two chunks, you're going to be fine. If you're at the start, you're also going to be fine. But if you're in the middle like this, the CPU is not going to be able to just load your integer. It's actually going to have to load two integers and do some shifting to recover your integer. Some CPUs will actually just do that if you try to make them load an integer that isn't aligned, but some others will just send a hardware exception at you. Some compilers, if they know you're doing unaligned stuff, will just tell the CPU to manually do all of that so that the CPU doesn't throw exceptions at you. But there are other types. Some types are very interesting. They basically are just a lot of types that you've just clumped together. And so here, you're just going to wonder, how do I distinguish these types? How do I distinguish my variants? And in fact, once I know which type I am, how do I recover that data? Finally, there are unit types. These are funny. They can only have one value. So if they can only have one value, why would you even store them in memory? Because you always know the value. In fact, if you don't store them in memory, does a reference to them even make sense? Or could you just say that they're all singletons, and so references could also be zero-sized? Well, let's see what C thinks about all of that. For structures, C has it pretty simple. Fields are always aligned unless you use a packed representation, and they are always in source order. That means it's very easy to be very wasteful with your memory. If you do a bad type layout like this one, where you have a U16, then a U32, and then a U8, you're actually going to waste 5 bytes, 2 in padding after the U16 to align the U32, and 3 after the U8 so that the structure's size is a multiple of its alignment, which is the alignment of its largest type. Instead, you could have just shifted the U8 before the U32, and then you just have 1 byte in padding, which is unavoidable for this structure, but you'd have saved 4. For some types, C has it also pretty simple. It just doesn't have them. So you're going to have to make them yourself, and since C is not going to help you whatsoever, you're usually going to want to keep them simple. To do so, you're going to do them as a tagged union. A union is just some memory that is reserved for a set of types, but you have no way of telling which type it is going to be. So what you're going to do is add a tag in front of it, an integer that's going to tell you you're currently within variant 0, 1, 2, etc. You're usually going to use an enum because that way you have a proper name for that. Finally, unit types. Conceptually, you can have them in C, but they're never going to be zero-sized because zero-sized types are undefined behavior. So you're typically going to represent them as a byte that you're just never going to read. So now let's have a look at Rust's default ABI. For product types, fields are still going to be aligned, but now the compiler is going to reorder them to try and minimize memory usage. For some types, tags may be put in a niche. Rather than having an external tag, if the compiler realizes that it can put it inside padding that is common to all your types, it will do so. It will also try and employ forbidden values. That way, if it knows that a type can't adopt a value and that the other type can contain that value, it's just going to use that value to signal you're currently not in the forbidden tag. Finally, for unit types, we have zero-sized types. However, references to them are not zero-sized. That's why we typically use unit types as a way to represent opaque pointers. Let's zoom in on Rust's sum types because they're actually the more interesting ones layout-wise. Say you wanted to have a string that may or may not be borrowed. For that, let's start and have a look at a borrowed strings layout, or a str. Typically, it's just going to be a start, which is going to be a pointer that can't be null, and a length. If you have a known string, it's going to be named string, and it's also going to have a capacity so that it knows how much it can grow before needing to reallocate. If you want to have a combination of these two, something that can be one or the other, typically you're going to use a cow in this situation. And if you're on a bad day, your cow is going to look like this. The first byte will be the discriminant, and it can be either 0 or 1, and then you'll have 7 bytes of padding if you're on a 64-bit machine, or just 3 if you're on a 32-bit one. And then you're going to have the union of your str or your string. But if the compiler is clever enough, and on a good day, instead what it will do is shift the str to the right by a pointer size, and say that before the str always comes a 0, because that 0 cannot be the value of the start pointer of the string. So that 0 is enough information to know that you are in a str and not in a string. And likewise, if it's not 0, you know that you're in a string, because you'll have guaranteed that you always put 0 there if you're in a str. Rust makes a few guarantees about its enums. First, references to variants can always be taken. If you're in a variant, you can always reference it and use it as if it was a reference to any other value of that type. So for our layout that we had for strings and strus, cowstr could never adopt this layout where string's start pointer has been moved all the way to the right to make this usage, because that would mean that a reference to a string inside a cow is not the same as a reference to a string in general. The other guarantee is that if there's only one niche in a type, then option will use that niche as none. That means that sum of t will always be represented by the same layout as just t. But are compact enums really that important? Well, for that, we'll just make a small reasoning by induction. Most enums have very few variants. Most of them only have 2, to be honest, but it's very rare for them to go above 10. But their alignment is going to be the maximum of their variance alignment, and most of them are going to at some point contain a pointer. So that means that on a 64-bit machine, more often than not, if you have an external tag, it's going to cost you 8 bytes to store typically 1 bit of information, which is very sad. It's not just sad. Larger types means that you have larger stack, and a larger stack means that you can store less states per cache line, which means that you're going to be slower. In fact, you're going to be much slower. Zeno has gotten 15% faster just by optimizing our layouts for some of our core types. Just by making some of these a couple bytes smaller, we've gotten a 15% speed increase. So, why would you want a stable ABI? Well, it's all to do with dynamic linkage, which comes in 2 flavors. With runtime linkage, you're going to load plugins, and typically in Rust, you'll interact with it through the lib loading crate. It's very useful to do combinatory packaging. If you have a lot of features, but you want to be able to deliver just a certain set to your clients, typically it's going to be very hard, and you're going to have a lot of release binaries if you link everything statically. Whereas if you link everything dynamically, you can just have your core binary and plugins for all of the features that you would have had to ship combinatorially with static linkage. It's also going to allow you to have multiple instances of a given symbol, which most linkers won't allow you to do because they will try to link globally, and if they see several definitions for a same symbol, they will tell you, I don't know which to pick, you sort this out. Talking about more traditional linkers, dynamically linked executables are load time linked. What they do is they just ask the OS nicely to link them with some libraries when they are loaded. It's very convenient to save memory on a computer, but more importantly, that means that if the system library gets patched, all the dependents get patched with it without needing to recompile anything. Whereas with static linkage, you will have to rebuild every single dependent to the library in order to fix a bug or a vulnerability. But dynamic linkage is not aware of ABI, and that means that linkeys must agree implicitly on ABI for each symbol. Otherwise, you're going to run into undefined behavior really quickly, because they will just not agree on how types are laid out or how a function is supposed to be called. And at some point, a field is going to get mixed up with another. For example, with a vector, the host might think that the first field in a vector is the length, but the plugin might think that it's the start pointer. If that happens, the host might send a vector to the plugin, which, when it attempts to read something, will dereference a length as if it was a pointer. Luckily for you, that will probably become a segfault rather than some more horrid behavior. So, is Rust's ABI stable? Well, no, not even close. Here's a list of things that may or may not affect your binary's ABI. The compiler version is kind of obvious, because that's the best way to change an ABI. Just change the compiler. But it can also change with compiler options such as optimization level, which may make it try a bit harder to get better layouts for your type or a better calling convention for some of your functions. And then there's z-randomized layout. Supposedly it's for security, but I think it's just there to take the piss at people who want ABI stability by showing them, hey, look just how unstable we can make ABI if we want to. But why? Why would you not want a stable ABI? Well, mostly it's for freedom. But it's not just freedom for freedom's sake. It's actually been put to very good use by the Rust compiler. In 1.65, niche optimizations have been made available to enums that have multiple data variants. Before that, you could only get niche optimizations when there was only a single data variant, which meant that before 1.65, you always had the sad cow layout. In 1.67, they tried and make field ordering a bit better by trying to make niches more accessible and easier to align for enums. But actually that broke the cow layout and it became fat again. So in 1.70 they fixed it and now we have small cows again. Yay! It's also a big commitment for the standard library to say that a type is ABI stable, because ABI stability isn't just about how the type is laid out in memory depending on its fields, it's also about, well, the fields. If you change a field, you're no longer ABI compatible. In fact, if you change an invariant about a field, it's no longer ABI compatible either, because for example, if the pointer of a box was supposedly allocated by libcmalloc and then becomes allocated by gmalloc, well, you're going to have location errors. So you need to stick to an implementation once you stabilize ABI, which is often a problem if you want to improve things. So we know why Rust ABI isn't stable, but we also know that C's isn't very good. So let's just make our own. So what features would we want in our stable API for Rust? Well, we'd want to support Rust's best features. One of them is trait objects. They're just a very convenient way to do what we typically do with opaque pointers in C. So you're going to also want to support closures because they're very idiomatic in Rust, and futures because they allow you to do things that you can't really do otherwise, at least not without a lot of headaches. You're going to want to guarantee compaction types because, like I said earlier, you can get great performance gains just by having them around. Finally, you're going to want to provide a proof of stability because if you want a stable API, you need to prove that you have stability. You want it to be easy to use because otherwise no one's going to put it to use, but you want it to be hard to misuse because the consequences are undefined behavior and you don't want that happening. Finally, you want a cool friendly name for it, so enter stabby. Stabby is a crate that you can download today from crates.io, and it's going to provide you with a stable type representation. It's available for any version of Rust that supports generic associated types, so from 1.65 onwards. It supports compaction types, and it also provides you multi-trait objects that can be passed over FFI safely. And most importantly, it has a spec, which means that if you wanted to, you could implement it for C++ or Zig and use that as an interop interface. So let's prove some stability. The way you do a proof in Rust is with traits. So let's create a trait, iStable. To be stable, you need to be sized, because otherwise you just don't really have a layout, so it's hard to be stable. Since you have a size, let's store it. Let's also store your alignment. And in fact, let's store your forbidden values and unused bits so that we can do niche optimizations by taking advantage of them. We're also going to store whether or not you have exactly one niche from the point of view of the Rust compiler, because that's going to tell us whether or not your options are going to be the same layout as you. Finally, we'll store a report about you for future purposes. If you're interested about how this trait only has types in it and somehow does computation, well, just come and see me at Rust Lab in November, and I'll tell you more about how to do math with the type system. But now we're going to see how stabbies get used. So how do you use stabby? Well, you just stabby all the things. For a structure, you stabby your structure, and it's going to imply that it uses the C representation, and it's also going to throw compile errors at you if you are being a dum-dum and doing suboptimal structures. Somehow C has existed for 50 years and there's still not even the lint to tell you that. Finally, it's going to derive iStable, which is going to let you use that structure in larger structures or enums, and stabby will be able to take advantage of all the information that iStable provides. If you put it on a function, it's going to force you to pick a calling convention, and it's going to check that all the arguments are indeed stable, because if your arguments aren't stable, your function isn't either. If you put stabby on a trait, well, it's going to give you the same guarantees for your functions, but now it's also going to do a whole lot of stuff. It's going to build a vtable layout for your trait, so that you can now have all your types that implement your trait give you a static reference to that vtable layout. That's going to be useful to construct trait objects. That vtable is going to exist regardless of if your parameters are or aren't stable, but the vtable is only going to be considered stable if all your parameters are. Finally, it's going to do a lot of boilerplate to make sure that you can use these trait objects kind of like they were normal trait objects. That actually requires quite a bit of code to be generated. But I just told you compact enums, so let's see how stabby does them. It actually does that by turning your enums into a balanced binary tree of stabby result. So it's going to look somewhat like that for a free variant enum. If you represent it as code, it's going to look like that. A structure that holds a result of a result of a result up until you get to the leaves, which are your variants. But how is that result represented? How is that one stable and not Rust's? Well, that result is basically just a structure that has a tag and a union, except the tag might be a zero-sized type whose only purpose is to inspect the union to tell you whether it is a certain variant or the other. That tag is computed by the type system with a deterministic algorithm, which is basically just going to check whether or not a forbidden value fits in the other's unused bits. If not, it's going to try and see if there's intersection between the unused bits, and if not, it's going to shift the smaller type by its alignment, and it's going to try that 8 times at most. That way, Rust's compiler is fully aware that this cannot recurse forever, which makes it very happy. But we just said that everything has become structures, and no less structures with private fields, so how do you pattern match on that? Well, you don't. But it's emulated. For example, if you want to match on a reference of an enum, stabby will let you emulate that by doing a matchref, which is going to take one closure for each variant and supply that closure with a reference to that variant if that variant is the one that's actually in foo. The other closures are just going to get dropped. It's less comfortable than normal matching because the borrow checker is going to be less friendly with you there. But it's better than nothing, isn't it? Stabby also implements a rather small form of reflection. That is a way to inspect the types even at runtime. That's what the report earlier was, and it's going to allow us to have more procedural macros. Stabby export is going to export not only your function, but also a report that's going to let us inspect whether or what the types that function was thinking of using. That means that when you stabby import that function through an extern block, stabby will in fact check whether or not the report coincides between the two binaries before letting you access the symbol. And you can also do that with libloading through import stabby, which is provided by a trait. But stabby still has limits. Like I said, you lose pattern matching on enums when you use the stabby representation, which is the default representation when you stabby an enum. It's emulated through matchref, matchmute, and matchowned, but if you see that representation stabby doesn't actually save you anything, you could just say that you want to use representation u8, still with stabby, so that stabby can still be used for bigger types that contain your enum. You cannot implement the stable trait for functions that have generic lifetimes. That's a constraint of the compiler because that would conflict with the implementations that exist for functions in general. And the main problem is that you can't coerce your dependencies into stability nor istableness if they're stable. There are escape hatches, so if you know that a type is stable, you can just say that it's stable like some other type and tell stabby what that type would be. That way, you don't have to worry that much about the orphan rule. But there's also safety guards, and these are going to be helpful if you don't know whether or not a type is stable, and these are called canaries. These are going to encode the compiler options into symbols that are going to be required by imports. That way, linkage will fail if you have different compiler options, which might save you, maybe. But stabby is not the only work in the field of ABI stability. To me, the founder of that field in Rust is ABI Stable by Roger Matty, but there might be some predating work. It also has a stable trait, and it seeks to provide an ABI stable alternative to stdlib. It also supports trade objects, although I think that ABI stables are a bit lesser than stabbies. Josh Triplett has made RFC 3470 Krabby to propose a cross-language stable ABI that supports a bit more of Rust. Notably, it supports slices, so you can now know whether or not the start or the length is the first field of a slice. It doesn't support trade objects though, and only few compact sum types are defined, kind of on a case-by-case basis. Marabos's RFC 3435 Expert is not so much to do with ABI and more with how we can make linkage more friendly in the language by integrating it. The goal is basically to just be able to mark a function with export, and the language is going to help you to import it without having to define import blocks. But all of these, stabby, ABI stable, these two RFCs, they all share a same problem when you worry about ABI. And that problem is that when you want ABI stability, it must be turtles all the way down. You cannot make a stable type out of unstable types. So if you have dependencies and you want to have their type within yours, well, you better hope they are ABI stable, because if they're not, you're not going to be ABI stable either. So you're either going to have to replicate them, or you're going to have to try and convince maintainers to do the pact of never changing ABI again. Good luck with that one. So here's my dream for dynamic linkage in Rust. First, it was simple. Just allow us to select a default API within cargo.toml. That way, you could say, well, anything in my code and my dependencies that hasn't specified an API, just use that API for it. I don't care if it's a bit less efficient. I want API stability because I'm doing something that relies on it. But that's a bit strong, and there's maybe a better option. We could expand RFC 3435 to say that when you export a function, you don't just export the function, you actually tell it which API you want it to use. And the compiler is going to be tasked with contaminating the types that are recursively in the function's signature. That way, the compiler could be tasked with only making the types that you need to be stable, but making them stable independently of how they were coded. That means you could have ABI stability as a pure feature of the final user, which would be very convenient both for library implementers and for the final users. So in conclusion, ABI stability is a hard problem. It's a hard problem to reason about, and it's a hard thing to implement. It's a large commitment to do, so in general, if you have a choice, do IPC plugins. Only do dynamically linked plugins if you really know that they're going to be your performance bottleneck. Otherwise, you're going to save yourself a lot of trouble by going the IPC route. Also, Stabby is very cool. It has a lot of features, some of them Rust doesn't even have yet, but most importantly, it's available today. And what I find really cool about it is that, to my knowledge, it's the first ABI as a dependency. The first time in a compiled language you could just say, well, let me just pull an ABI from my package manager. But I really hope Stabby becomes obsolete soon, because while it's cool, it's mostly a symptom of the fact that Rust's user story for dynamic linkage still needs a lot of polishing. But luckily enough, efforts are ongoing, core team is looking at it, and in general, we can hope that at some point Rust gets as good a story for dynamic linkage as it currently has for static linkage. So I thank you all for your attention, and I hope to see some of you IRL at Rust Lab in Florence in November. Take care, bye.